Hello everyone, my name is Leyla Gadbegi. I have PhD in Material Science and Engineering. Today I'm going to explain how N-Channel MOSFET is being made. The starting material for making N-Channel MOSFET is a P-type silicon wafer oriented in 100 plane. Monocrystalline wafer silicon is being made by melting pure polysilicon at 1400 degrees Celsius in a sealed furnace. First, seed crystals of the size of a pen are being introduced into the melt. As silicon is being cooled, the ingot is slowly withdrawn. The final ingot is pure monocrystalline silicon. The ingot is finely cut and polished to make a silicon wafer. Formation of wafers require a series of steps consisting of deposition of oxides, deposition of metals, implantation, and patterning. Implantation and patterning require lithography. In this lecture, I assume that you know lithography. Starting from P-type silicon oriented in 100 plane, first, silicon oxide and silicon nitride are deposited on the wafer by chemical vapor deposition. Next, a layer of photoresist is applied on top of the oxide. Using a mask in a lithography step, the extra photoresist will be removed and the active device area will be defined. Next step is making channel stop. If you don't know what is the channel stop, a channel stop is a layer of high concentration P-type semiconductor that prevents surface from inversion and eliminates conducting paths among neighboring layers. To form the channel stop, boron ions will be implanted. Because of segregation effect, most of implanted ions are pushed underneath the oxide layer. The third step is forming the field oxide. You may ask, what is field oxide? The field oxide isolates transistors from one another. To form it, first, silicon nitride not covered by photoresist will be removed. Then the photoresist itself will be removed. Next, the wafer will be oxidized. As a result of oxidation, oxygen penetrates into the silicon and converts some of the wafer into the oxide. Here you can understand why we need silicon nitride. Because silicon nitride is not an oxygen ion conductor, the area beneath the silicon nitride won't be oxidized. The fourth step is to make the channel by implanting the active area by boron ions. This step has an important role in determining the threshold voltage. For enhancement mode MOSFET, boron ions are implanted to increase the threshold voltage to a predetermined value. The next step is to form the gate oxide. Forming gate oxide is done by depositing 10 nanometer silicon oxide. This step is very important in determining threshold voltage. To complete the gate, polysilicon is deposited on the top of the gate oxide and heavily doped by phosphorus ions. And of course, transistors need source and drain. Oxide grown during previous steps will play as a mask in this step. Arsenic is implanted to form the source and drain. The temperature is very important in this step. If a low temperature can be used, the gate source and gate drain capacitances can be much smaller than gate channel capacitance. Finally, metallization provides contacts. It requires first deposition of pig glass. Pig glass will be flowed by heating to make a smooth surface topography. Then contact windows are defined and etched in the glass. And lastly, a metal layer such as aluminum is deposited and patterned. Thanks for watching. My reference for this presentation is Fundamentals of Semiconductor Manufacturing and Process Control by Spanos and May.